Now we'll study the concept of equilibrium. As I think all of you know, equilibrium implies no force or sum of all forces acting on body is equals to zero. This is called a state of equilibrium. Now, when we talk about conservative fields, in conservative fields, we already studied that force can be written as minus of du by dx I cap. This is the force vector acting on an object. If U is the potential energy and F is the force applied by the field on the body. Now, in conservative field, when a body is in equilibrium, we can simply state when a body is under the state of equilibrium in conservative field, then we can simply state force acting on it, which is mod of du by dx. This must be equal to 0. If force acting on the body is equals to 0, that means the rate of variation of potential energy should be 0. If du by dx equals to 0, this can happen under three conditions. The very first thing, if U is a constant, then it is possible that derivative of potential energy with position is 0. Second condition is, if U is maximum, then also we can state differentiation of potential energy with position is 0. The third case is if U is minimum. So we can say there are three conditions under which the body in conservative field will be in equilibrium, that is either potential energy is constant, or it is maximum, or it is minimum. All the three cases we are going to take up one by one. Let us consider first case where we consider potential energy is maximum. In a system, if we talk about potential energy which is given as a function of position, and say if we plot the graph between potential energy and position, say the graph comes like this. Here we can say there will be a position x equals to x1 where we can say the value of potential energy will be maximum. At this situation, if we just plot the slope, we can simply state the tangent of curve at this point is horizontal, or we can say at this position du by dx is equals to 0. So we can say simply at x equals to x1 the slope of graph is 0, or the force acting on an object which is mod of du by dx, that is also equal to 0. So this is the state of equilibrium. In this situation, if we just analyze the equilibrium position in the neighborhood of this position x equals to x1, this position before x1 we can call x1 minus, and just after x1 we can call x1 plus. So if at the position of equilibrium, if a body is there, we can say no force will act on it. If at a slightly higher position, or if we displace the body toward right at a position x equals to x1 plus, we can see at this position the tangent will be negative, or you can say the tangent is making an obtuse angle with the positive direction of x-axis, or we can say at this point the slope will be negative. If we find out the value of force vector at x equals to x1 plus is slightly higher value, this force can be written as vectorially it is negative of du by dx I cap. You can see at this position the slope is negative. If du by dx is negative, you can see this minus du by dx, this comes out to be a positive quantity. That means the force vector will be positive in this situation. If force is positive, at this point body will experience force toward right. Similarly, if we calculate at x equals to x1 minus, that is slightly before the equilibrium position, at this point if we just see the slope, we can simply see it is making an acute angle with the positive direction of x-axis, so du by dx will be negative. Here we can say at this point du by dx is negative, and at this point du by dx is positive. We are talking about the neighborhood of equilibrium position slightly after and before this. So here if we calculate the force, this minus of du by dx I cap. If du by dx is positive, we can say the result will be negative. This shows at this point when body is displaced slightly before the equilibrium position, it is slightly displaced at a position which is before this x equal to x1. We can see the force acting on the body is negative. So at this point body will experience force toward left. Here we can state when body is slightly displaced from the equilibrium position in either direction, the force will be acting on it away from the equilibrium position. So if you displace the body, body will have a tendency automatically to move away from the equilibrium position. And it is quite obvious because in previous section we have studied that in conservative field, forces act in the direction where potential energy of body decreases. So at the equilibrium position, potential energy is maximum. If you slightly displace the body, we can see toward the side of equilibrium position energy is increasing and away from it energy is decreasing. That's why force is acting in a direction away from it. Similarly, if we displace it at a position at x equals to less than x1, again potential energy is decreasing toward the side where x is decreasing. So force is acting in the away direction. So if body is placed at x equal to x1, it will be at rest. If you displace it slightly, it will have a tendency to move away from the equilibrium position. That's why we say at x equals to x1, body is said to be in unstable equilibrium. This type of equilibrium we call unstable equilibrium because if body is in equilibrium and it is slightly displaced, then body will have a tendency to move away from the equilibrium position. It is disturbed forever. That's why it is said to be in unstable equilibrium. Now if we discuss our second case for the equilibrium position where potential energy is minimum. Say if in a situation potential energy is given as a function of x, if we plot the graph of variation of potential energy with the position and say the graph looks like this. In this situation at a particular position, say x equals to x1, potential energy of body or the particle is minimum. We all know that lowest potential energy state is said to be the most stable state. Here we can see the tangent is horizontal. That means at this point du by dx is equal to 0. This shows that at x equals to x1, in this case, the force acting on the particle which is minus du by dx I cap, or in magnitude we calculate it as 0. So this is the point of equilibrium because net force acting on the body due to conservative field is 0. Let's analyze the situation if we displace the body, what will happen? So if body is at x equal to x1, it will not experience any force. We displace it slightly at a position where x is more than x1. This say x equal to x1 plus. Here we can see potential energy is increased. We just see the slope, we just see the tangent. You can see it is making an acute angle. But for this tangent, du by dx is positive. So we can say at x equal to x1 plus, force factor is minus of du by dx I cap. Here du by dx is positive, this implies this force is negative. So this minus of du by dx and du by dx in this case is positive. So force will be a negative quantity at this position. So if a body is displaced from equilibrium position to the neighboring position where x is increased, it will experience a force that exists in negative direction toward left. Similarly, if you displace it toward left, that is at position x equals to x1 minus, you can see the slope of this graph is negative. So at x equals to x1 minus, we can see force vector is minus of du by dx I cap, and here du by dx is negative because slope or the tangent is making an obtuse angle with the positive direction of x-axis. So if du by dx is negative, we can say this force will be a positive quantity. That means if you displace the body from equilibrium position slightly toward left, it will experience a positive force vector that is toward right. So here we can say when our body is displaced from the position of lowest potential energy, if you displace it, body will have a tendency to come back to this most stable state by the field forces. That's why such an equilibrium we call stable equilibrium. Like in the previous case we have studied, when potential energy is maximum, body will have a tendency to move away from the equilibrium position, and that equilibrium we call unstable equilibrium. Here body is said to be in stable equilibrium, which is the position of minimum potential energy. So be careful about both the cases. Where potential energy is minimum, equilibrium is said to be stable. When potential energy is maximum, equilibrium is said to be unstable. Let us analyze the last case of equilibrium, that is the third case, which corresponds to the situation when potential energy is a constant. So in a particular region, potential energy does not vary with the position, and say this graph looks like a horizontal straight line. So we can say that all positions the potential energy value is constant, say it is U0. So we can say if the graph is horizontal, everywhere we can state potential energy is constant, and we can write the force acting on the particle, which is mod of du by dx. This is equals to 0 because the slope of this horizontal straight line is always 0. In this situation, say between 2 points x equals to x1 to x equals to x2, if the potential energy is constant, maybe after x2 it is dropping, maybe before x1 it is increasing, and if a body is placed somewhere between at a position x. Now we displace the body whether at a higher position of x or at a lower position of x, we can see that everywhere the force remains 0. So if you displace the body from one position to another, body will not have any tendency to move neither away nor towards the previous position, because the new position is also the equilibrium position. Such an equilibrium we call neutral equilibrium. So when our potential energy of body is constant in a region, we say for all positions x which is less than or equals to x2 and more than equals to x1, body is said to be in neutral equilibrium. If just beyond x1 and just beyond x2 potential energy varies, we will not include this equality sign in this case. So when our potential energy is constant in a region for all points excluding the extremities, the body is said to be in neutral equilibrium.